Thank you for the introduction, Asta. Today I'll be presenting about Virtuoso, which is a new TCP stack targeted for virtualized environments. Let's start talking about the role of virtualization in cloud computing. In the cloud, guests run as virtual machines and containers. The cloud leverages the virtualization to improve resource utilization of the networking stack and ensure security and performance isolation for guests utilizing the stack. But there is one problem. Namely, current architectures add significant performance and resource overheads to the networking stack in favor of isolation. And I'm going to show how current implementations for virtualized network stacks lead to this trade-off. So the current status quo is that you have these layered and siloed stacks, where each guest runs an independent network stack. This is good because it silos applications and minimizes inter-VM performance interference, but it over-provisions resources. The second issue is that you have network virtualization implemented as a deeply layered architecture, where it's good because it simplifies development, configuration, and management, but it adds overhead. So now let's look into detail why layers and independent stacks lead to over-provisioning and overhead. So for the sake of this talk, we're going to use virtual machines as examples for our guests, but our work also applies to containers. And what happens is that you have, in a virtualized environment, you have a virtual machine monitor that abstracts the hardware and manages the resources. In traditional computing, instead, what happens is that OS has direct access to the hardware. The VMM allows multiple tenants to run applications on the same host and share physical resources, thus becoming the backbone of the modern cloud. So now let's look at how this leads to a layered architecture. In the layered implementation for the virtualized network stack, a virtual switch runs on the lowest layer on the host and sends and receives raw network packets. The virtual switch will then forward packets to the guest network stack. At receive, packets from the virtual switch are receiving the guest VNIC, and for transmission, the VNIC passes packets from the guest to the virtual switch. The consequences of this are that the layers simplify deployment with different implementations. But crossing layers and boundaries adds overhead, leads to duplicated work, and wastes precious CPU cycles. And now that we have looked at the effects of layering virtualized environments, let's look at how we end up with these independent and siloed stacks that I talked about before. On top of layering, another artifact of current virtualized implementations is independent stacks. And with siloed stacks, each guest runs a separate network stack instance that interfaces with a VNIC. Most clouds will dedicate fixed cores to VMs for isolation and performance. For instance, with the typically bursty workloads you have with VMs over-provision to handle the peak load. And for communication-heavy VMs, most cycles are used for network processing. Static allocation leads to low resource utilization because CPU resources cannot be flexibly reallocated from idle VMs to VMs experiencing bursts. And right now, with these graphs and diagrams, I have illustrated the challenges imposed by layered and siloed stacks, so let's summarize them. So there's basically two challenges with layered and independent stacks. The first one being the trade-off between isolation and resource utilization. And early multiplexing independent stacks facilitates isolation but reduces its utilization because the resources cannot be pooled at lower levels. Second, layer provides modularity, but crossing layers and boundaries reduces performance because of intermediate queuing and duplicated work. And as a solution to these challenges, I present Virtuoso. Virtuoso is a new TCP stack that is aimed at virtual machines and containers. And it addresses the two challenges that I talked about before. First, it reduces overhead by squashing layers and having a one-shot fast path. It guarantees isolation by performing fine-grained scheduling, and it improves resource utilization by sharing the network stack. I'm going to show how I address each one of these points. So let's start by looking at how we reduce overhead. So the main idea behind Virtuoso is the single-layer data path and one-shot fast path. And Virtuoso bypasses the guest operating system and the VMM by using fastpath for transmit and receive operations. Control operations and exceptions go through a separate slow path because we realize these operations do not affect the general performance of the system. On top of that, one-shot processing saves information such as a tunnel ID and tunnel IP addresses so that subsequent packets for that flow can use this cache information and improve performance. By combining both a fast path that bypasses the OS and the virtual machine monitor with a one-shot fast path that caches network virtualization state, we're able to significantly reduce the number of cycles spent with each packet during transmit and receive. And this ends up leading to average latencies that are 2.2 times faster in Virtuoso than standard virtualization baselines. Next, I'm going to show how fewer and relatively consistent processor cycles per packet help us perform fine-grained scheduling and maintain isolation. So in Virtuoso, we identified three main CPU-intensive tasks for the guests. These tasks are polling guest transmit queues, what we call the poll phase, packet transmission, the TX phase, and receiving packets, the RX phase. We measure the cycle spent in each one of these phases and assign a budget to each guest. Schedulers on the poll and then transmit phases use this budget information to schedule packets. And this budgeting and scheduling mechanism guarantees isolation between guests by preventing VMs that deplete their budget from doing more work. So now let's look at how well we guarantee isolation. In this experimental setup, we start two VMs. One VM is an aggressor VM that attempts to introduce performance interference by increasing the size of the messages that it consumes so that it consumes more resources. The second VM is a victim VM where we measure the 99th percentile latency. Solid stacks such as OVS tasks that run one independent instance of the task TCP service per VM maintain isolation and are the ideal scenario. Using the regular task stack that shares the networking stack between applications increases latency. But Virtuoso, on the other hand, maintains 99th percentile latency the same as the solid stacks, despite sharing because of the fine-grained scheduling mechanisms that we implemented. Now that we have looked at how I guarantee isolation in Virtuoso, I'm going to show you how I share the stack to increase resource utilization. So the main idea behind increasing resource utilization in Virtuoso is sharing the network stack so that we can provide elastic resource utilization. What we do is that we remove the networking stack from the guest OS and instead share the stack between multiple VMs. Remember that I talked about before how solid stacks over-provision resources. So Virtuoso improves utilization by consolidating resources and being elastic. This happens because pooled resources allow us to serve the same workload but with fewer cores. And this is basically how we improve resource utilization with Virtuoso, by using shared stack. So now let's look at how much we improve it. In this experiment over here, we start 4 VMs running echo servers that respond to RPCs from clients. And then we measure the aggregate throughput of the VMs when 75% of the VMs burst at the same time. The OVS task baseline is saturated and is assigned a total of 4 cores for the networking stack, 1 core for each task instance in a VM, and we measure the total number of requests per second for this baseline. In the setup, we assign 3 cores to Virtuoso and the networking stack, and our results show that we are able to increase throughput compared to the baseline, even when using 1 less core in total because of the stack is shared. I have now covered the 3 main contributions in Virtuoso, so now let's review them before wrapping things up. So Virtuoso tackles the 2 challenges from network virtualization that I talked about before. It reduces overhead by using the single-layer data path and one-shot fast path that leads to us spending fewer cycles per packet. Second, we provide the same isolation as shared stacks because of our fine-grained scheduling. And finally, we improve utilization by sharing this TCP stack, which leads to 50% improvements in utilization. And thank you.
Question?
Ed Bugnon with EPFL, great work, super interesting. The one thing you have not talked about is on which core do various pieces of the functionality run. And to put it into perspective, in the traditional hypervisor design where you have a virtual switch, those designs were traditionally associated with a very symmetrical view of the world, where the networking stack and all the networking functions, including the virtual switch, actually runs on all of the cores of the system, and basically RSS reception and independent transmission rings lead to that model where the networking functionality runs everywhere on every single core. And it seems, in your case, but you were not very explicit about it, that you actually have a much more asymmetrical design, where basically some cores are dedicated to networking and the others are free to do compute. Is that a correct understanding?
Yes, thank you for your question, Ed. That is correct. So in Virtuoso, we have dedicated cores for the networking stack. Specifically, we assign them between slow path cores, which we have one that does the slow path processing, and then we have fast path cores in the data path that can auto scale as the networking throughput increases or decreases, but they're dedicated to the networking stack.
Thank you.
Nice talk, thank you, Dimitri, and to you, Singapore. My question is about what kind of application, what is the class of applications that you are looking at, particularly, for which this system can be most beneficial?
Thank you for your question, Dimitri. So Virtuoso specifically target, I think, a large set of data center applications, but specifically applications that are sending short messages, so like small RPCs, but they also have long pre-established connections.
Would it work well for HTTP level services? Because in data centers, it's mostly HTTP level fabric with service mesh.
I imagine it could work. I have to look into the details of was it HTTP services that you said?
Yeah, most of the services are exposed to the HTTP endpoints.
Yeah. So I think if they are not short-lived, so one of the Achilles heels of our product is specifically short-lived connections. So given that we go to the slow path for opening and closing connections, if you're opening a lot of short-lived connections, we're going to have overhead that's worse than some of the baselines. But if, I don't know the characteristics of the HTTP workloads, but if they don't have these characteristics, I imagine we'd still be good.
Thank you.
I think we'll be able to take one quick question.
Okay, Ming Li from SJTU. By introducing shared TCP stack between VMs, will that make it harder to achieve inter-VM performance isolation? Because the network is shared.
Yes, and I think that's where one of our main research contributions is that given that we share the stack, we do all this fine-grained scheduling that we're able to maintain, guarantee that there's no performance interference between the VMs. Specifically, at least in one of the slides, I showed how we have the same isolation as some siloed stacks, where you statically partition cores per VM, which would be like the state of the art for maintaining isolation.
Okay, thank you.
Okay, thank you.